The moon forming impact. Did it kickstart plate tectonics on Earth? Did it affect early life on Earth, early oceans? How did this planet resetting event affect Earth and its evolution since? Chris and Jesse from the Planet Geo podcast collaborated with me about a year ago on 2 videos related to the Earth's oldest rocks, and one of the things we covered briefly in those videos was the moon forming impact. But you guys had a lot of follow-up questions about this impact and how it affected Earth and the moon itself. And so in this video, Jesse and I are going to be attempting to answer these questions. So let's jump into it. We are going to jump right into the weeds of it with this first question. Then this was a very, very commonly asked question. Did the moon forming impact cause plate tectonics?
Okay. Can I ask a quick question about the question? How common? I mean, you said you had like over 800 comments or questions about on this video. How many
Yes.
times, how many times did this come up? Broadly, question
This
like
one,
this.
well, especially so we had the two-parter. The first video, not as much, but the second video, we talked about the moon forming impact with
Oh,
Chris. And
okay.
so then it came up a lot more because we talked
Okay.
about the moon forming impact. We talked about early plate tectonics and how on early Earth, plate tectonics may not have been the tectonic regime. And so then that
Yeah.
brought up, I think, a lot of questions of, well, what did cause the beginning of plate tectonics? Could it have been this large impact? So,
Right. Right. Okay. Gotcha. Well, all right. I'm curious your thoughts on this, but my short answer is no. No, in the sense that the impact did not kickstart plate tectonics in that way. But it is a really interesting question. Why does Earth have plate tectonics and something like Venus does not? They're very similar kind of planets. Venus is Earth's toxic twin. And does it have something to do with having a moon? In tidal forces or the planetary resetting event that the moon forming impact caused, maybe that reset the planet at a time when it was cooler, and so maybe there's some trickle down effects that led to plate tectonics, but the event itself did not kickstart it. I think is probably what the question is kind of
yes.
implicitly assuming.
Which is, yes, and that's my understanding as well, because the moon forming impact, I mean, it was very large, and to my understanding, it melted everything
Yeah,
pretty much. There was like a global
yeah, yeah.
magma ocean. Okay.
This is a global planetary resetting event, even if it's like an indirect hit. If the impactor hit the Proto-Earth, even if it hit a glancing blow or something, it's really a planetary resetting event. This is melting the entire mantle. If it wasn't melted already, it's remelting it, it's resetting. Cores are merging, perhaps. So the impactor's core maybe merges with Earth's core, and some of the core material gets spit out. And so there's all these things, but it's a massively energetic event that is a planetary resetting event. I kind of
Okay.
think of like, Star Wars Death Star kind of stuff. Like, this
Yeah.
is a serious event for a planet.
Yes. And just to put some sort of timescale on it, it's also my understanding that plate tectonics, whether you go with the really, really old potential start date of like 4 billion years ago or almost 4 billion
Yeah.
years ago, or even the newer, 2.5 billion year ago start date of plate tectonics, both of those are millions,
Yeah.
hundreds of millions of years after the moon forming impact. So plate tectonics started much later.
Yeah, it depends. Yes, I think as with all these things, depends who you're talking to. But yeah, we,
Right.
we have, we have a couple of fragments of mineral grains preserved from a period 100 million years after the moon forming impact. Like that's it. That's all of our
Yeah.
record on Earth. So
Yeah.
we
So
really don't know. My opinion or my take on it, my interpretation of the current data, let's say, is that, 3.8 billion, which is 300 or 500 million years after the moon forming impact. There's a significant amount of time here. But yes, you're right that there's a
okay.
there's a bit of
So
a time lag.
yeah, a very long time after,
Yeah.
at least on human type scales. Even on
Yes.
early
Yes.
Earth, that was relatively fast. But yeah, and so the other kind of follow up onto if the moon forming impact didn't directly cause plate tectonics to start on Earth, could it have maybe triggered mantle convection, and then plate tectonics
Yeah.
was a result of that? Could it have started like the chain of events that led to plate tectonics?
hmm Again, no. And I think we have to sort of think about what mantle convection is, and that'll explain the answer no. Is mantle convection is just the Earth losing heat. It's a lava lamp. It's the lava lamp getting heated up from below, and then it's circulating. Hot stuff rises, cold stuff sinks broadly. I mean, that's an oversimplification, but it broadly
Yeah.
works here. So back in time, we talked about last time, I think that the mantle was probably a lot hotter. So convection was probably happening maybe even faster or more convection was happening. So the mantle's convecting. Any planet that is a quote unquote tectonically live planet has some kind of convection probably happening on it, or some transport of hot stuff from down below up to high.
Yeah. And
So,
I actually, after having looked through our notes on this and what you had added, I came up with another question that I'm sure was
oh,
asked and
okay.
I just missed it. Because everything that I read says the same thing. Essentially, any body with heat should have some sort of, convection. And so I'm curious, was there a time when like the moon had convection? Because when you look at the simulations of the moon forming impact, they were both like pretty molten for a while. And
Yeah,
and
for
so
sure.
why didn't if our Earth, if the progression of events was kind of the convection of the mantle, eventually plate tectonics, why didn't the moon ever evolve plate tectonics?
It's a great question. There are models, I think, for this, and it has to do with how quickly the planet cools effectively, and whether
Okay.
there's water or not water. And the classic thing, the classic petrologic thing, is that the moon has this anorthosite crust, which is plagioclase feldspar crust. Then the idea there is that when the moon accreted after the impact, it's fully molten, magma ocean planet, planetary body out there, and it cooled down. Surface cools really quickly because it's exposed to space with little atmosphere, or did not have too much of an atmosphere. So that cools pretty quickly, but basically the magma ocean starts to crystallize. There's debate about whether it starts top down or bottom up or middle out crystallization. But basically, the plagioclase in a magma like the moon, a basalt or an ultramafic composition that has very little water on it, plagioclase will float. And so that stuff floats to the top and becomes kind of a flotation cumulate. That's one model for the
Oh,
plagioclase float. So the reason we have more rocks from the moon that are older than almost all the rocks on Earth is that it didn't have plate tectonics, and it kind of maybe fully crystallized and was not big enough to maintain this thermal engine
right.
that might have kept an atmosphere around. You probably have to have an atmosphere to have water, to have plate tectonics. Like there's all these feedback loops. There's not one
Okay.
defining feature that says this makes a planet that has plate tectonics, but the
Right.
moon probably didn't. And it took 10 to 20 million years roughly to crystallize the magma ocean on the moon, likely, is kind of what some
Oh,
models suggest,
wow.
just like heat loss mechanisms. So,
So pretty
yeah.
quick
But yeah,
compared to Earth, which is still
compared
cooling.
to Earth, and it depends a lot on what you think about the atmosphere. If there's an atmosphere, if there's like a silicon
Oh.
vapor, if you have an atmosphere, it's an insulating blanket. So if there's any little atmosphere around there, it helps insulate and keep the magma ocean melted for longer, because it's basically like another heat exchanging layer on top of it, a little insulating blanket. If it's exposed just to space, it cools much quicker.
So for
Yeah.
that time when it was cooling, it had some sort of maybe mantle convection, some sort of tectonic regime where it was losing heat, but it wasn't plate tectonics. It was just loss of
Right.
heat mechanism.
That's right.
Okay.
That's right. Melt moving up and volcanism, and we there is younger volcanism on the moon, so we know that there's heat getting out because
Hmm.
we know that there's volcanism there happening. So that's one indication that there's still melting going on down at depth in some way, shape, or
Oh,
form, and heat is being
it's just
lost. So
not.
yeah, there are other ways to do that. But back to the moon forming impact and Earth. What that did do is dump a bunch of heat into the mantle. So the mantle was probably convected, was already hot, but it remelted the mantle, which is adding heat, and it probably fully melted the Earth, at least the mantle part of the Earth.
Actually, that brings up one point. I feel like the mantle is often depicted as this red magma.
I hate the color schemes. The color scheme we use in the textbooks as putting the mantle as red or orange drives me nuts because it gives you this idea that it's magma, right? And
Yes.
it's not today. I
Okay.
mean, there is a little hints of it around, but it's mostly solid.
It's solid.
It's hot plastic is kind of
Okay.
the analogy
Hot
for
plastic.
what it
Okay.
behaves like. Yeah.
That's a
So
good, yeah, that's a good analogy. So it was solid or becoming mostly solid before the impact, and then the impact hit and it remelt. Is that what we're
yeah,
saying?
that would be one idea. Yeah, exactly. Dumps a
Okay.
bunch of heat back into it, and that
Oh,
does remelting. So this impact is so violent, so much heat is added that it does planetary remelting, planetary resetting.
okay. So it did
Yeah.
reset things, but to our understanding, Earth it would have absolutely had some sort of mantle convection no matter what, and then it would have also probably had plate tectonics without the moon forming impact. Everything probably would have happened the same, even if the moon forming impact didn't happen in terms of
Yeah,
tectonics
maybe.
on Earth.
Maybe it's an open question, right? I mean,
Yeah,
what
yeah,
like how much volatiles and atmosphere, that's an important aspect of
yeah.
this. So if you have
Oh,
one magma ocean event, that's one time for the mantle to lose all of its gases. If you have two magma ocean events, that's a very different like mantle gas concentration world you live in. So a lot of this has to do is where did our volatiles come from? Where did our atmosphere come from?
yeah.
Because that to maintain a habitable planet for a long time you probably require something like that. So, but it's really, to my knowledge, and again, I haven't been kept up on the habitability literature for the last 5 years or so, but to my knowledge, that was very much a big question in the earth sciences is how important was the moon forming impact or even just the presence of a relatively large moon, how important is that for habitability of the planet? And plate tectonics is kind of tied into that habitability question a bit.
Oh,
So it wasn't the starting gun for plate
right,
tectonics, but it could have done something, maybe forming a moon, maybe bringing a bunch of volatiles, maybe outgassing the mantle, done
right, right.
something that helped eventually maintain the planet for longer in the way that Venus did not. Venus could not have
Oh,
maintained. So the difference between Earth and Venus, one big difference is, hey, we got a moon. We had a moon forming impact. Like, so how important is
oh,
that? I think it's a big
that's a
open
great
question
point.
for sure.
Yeah,
But
yeah.
it's one of those things that is a major difference between Earth and Venus at the moment. So
Oh, okay. So maybe
yeah,
it had changed something that set us on
yeah.
this track. We just don't really know exactly
We don't
what
understand the yeah, the
and
feedback
how
loops
important.
are
Okay.
really, yeah, exactly.
Very interesting. Okay, so, aren't there students out there that's interested in
Oh,
this? Very
it's a
open
rich,
research.
there's a lot of it's a lot of job security because we don't understand a lot, right? So
We need more
yeah,
research. Amazing.
absolutely.
Okay, so, and we kind of hit on a little bit of this, but another viewer question that I only saw one time, but was very
Okay.
intriguing to me because I think it brings up an interesting distinction was which is older, the moon or Earth? And other viewers also asked a different but related question: how quickly did Earth start solidifying after the moon forming impact? And you talked a little bit about how quickly the moon started solidifying after this impact. But I
Yeah.
think what's really interesting here, I think the answer to what is older, the moon or Earth, is different than what's older, Earth rocks or moon rocks,
Ah, yes.
because
Okay. That's a good point.
like again, the Earth was there before the moon hit, so technically the Earth is older. But then when it hit, it reset the rocks, and so the rocks took longer to cool, and then Earth rocks are technically younger than moon rocks because of
Yeah.
the cooling after the event. But then in our notes, you put that Earth there before moon is actually called Proto-Earth. So
Yes,
is
yes. All right.
Proto-Earth different than Earth?
Well, okay. So Proto-Earth, I'm gonna get the numbers a little bit wrong here because I forget exactly what they are. But Proto-Earth is Earth before the moon forming impact, okay? And that's smaller. We think that's substantially smaller than Earth as it is today. I don't remember the numbers, 70%,
Oh,
80% smaller, right? And then mass was added, then this impactor, which we call Theia,
yeah.
came in and hit. That's the body, the Mars-sized body that hit Earth. And then a whole bunch of materials kind of blasted off during that impact. Let me back up. The moon today has a smaller core as a proportion of its size than Earth does. And
Okay.
that's always kind of been hard to explain. One way that the giant impact model explains this very nicely is that the impactor, Theia's core, would have, because it's so big and dense, it's kind of like a bullet, it would have just penetrated the mantle and merged with Earth's core mostly. So there's models that kind of say the cores
Whoa.
kind of merge together. There's a whole bunch of stuff that's thrown off
Right.
during this impact, and Earth keeps spinning. Now we have Earth, so the combination of the two is Earth, but there's a whole bunch of debris around Earth, and that stuff aggregates to form the moon. And there's less iron in that stuff than there is in Earth because a lot of the Theia's core went into Earth's core, and some of it got spun out. So this is like a homogenization, mixing, and then separating the two bodies kind of an idea. And the reason that the impact model is a really compelling one is that we look at the chemistry of Earth and Moon, and they're chemically nearly identical. There are
Yeah.
small differences, small but important differences in the chemistry of Earth. It's different than Mars. It's different from Venus. It's different from Mercury. It's different from a bunch of meteorites. The isotopic composition in a bunch of different isotope systems, there's very small but very significant differences between the planetary bodies that have to do with where the planet formed in the radius of the sun. And so the Earth and Moon being so similar probably means that we had to we mixed them together at some point. That the Moon came
Yeah.
from some mixture of Earth, or some combination of the two. So we call Earth before the impact Proto-Earth. The impactor, the thing that hit, is Theia. Then we have, after the impact, we have Earth and the Moon. That's kind of the.
Okay.
And so Proto-Earth, we have no information. We have nothing left from Proto-Earth. We have nothing left from Theia because they got mixed together, melted,
Yeah.
totally destroyed. The Moon then cooled quickly, had this magma ocean body, cooled relatively quickly, 10 to 20 million years. We have a bunch of rocks from there because not much has happened to the Moon since that time. Since it cooled, impacts have hit it. There's been some volcanism, but there's no plate tectonics. It hasn't been resetting itself for 4
Right.
billion years. Earth, on the other
Right.
hand, probably crystallized some rocks on the surface very quickly after the moon forming impact, had some crust around, but that stuff has been totally reset by plate tectonics over the last 3.8 billion years of planetary resetting. That plate so the reason we don't have older rocks from Earth is almost certainly due to plate tectonics since that time, rather than like anything to do with the magma ocean phases there. Sorry. Okay, that was a long
Okay.
diatribe, but I just want to kind of set the stage for the
Yeah.
terminology that's used here, because it can be massively confusing.
Okay. Hold on. Back up a second. You
Okay, all right.
said that Earth, Proto-Earth,
Yeah,
was 70%
I
smaller
might I might not
than.
get these sizes right.
Okay. But
But there's
smaller than.
smaller because there's like a Mars-sized body that hits, and the moon right now is smaller than that. So the Earth was not
Right.
its full
Uh,
complement. The impactor added material to Earth, and what was spun out, some of that started to orbit around and then kind of aggregate into the moon relatively
right.
quickly. Yeah,
Yeah. So I'm curious. Now I'm trying to remember how much smaller Mars is compared to
oh,
Earth
that's a good
because
question. Yeah.
I've always pictured this as being Earth was the larger body and then the Mars sized impact. Was the
The
Mars sized object larger or
proto no,
smaller?
Proto-Earth was still larger.
Oh,
um
okay.
but more of that ended up in the Earth than in the moon, if that makes sense,
Oh, and we
broadly.
know they're
Yeah.
very chemically similar, as you mentioned, and this is one of the big proponents of the impact hypothesis.
Yeah.
Are there any slight or strong chemical differences? And if so, what do we think they mean?
There are tiny, tiny ones. I think it's debated what they actually mean. I think it's in the triple oxygen isotope system. There's some chemical differences, but the
Yeah.
Earth and the Moon are very, very similar in a bunch of different
Okay.
ways, apart from maybe one or two chemical signatures. And I believe one of them might be triple oxygen isotope composition. So the relationship between the 18, 17, and 16
Right.
isotopes of oxygen. Again, this is going back a couple years, so I'm not entirely sure about that. But I actually did see a recent paper this fall, I think, came out. They looked at, I think it was iron isotopes from Earth, moon rocks, and meteorites. And their model was that Theia, this Mars-sized thing, actually came from the inner solar system. So it's kind of an inner solar system body that came in and hit, which kind of makes some sense. It's a rocky body with a
Yeah.
core, probably. So
So we think that Theia had a core before hitting Earth?
Probably just because most differentiated meteorites of some
Uh,
body size end up
a
having a
certain size.
core.
Right.
Yeah,
Right.
they just
Okay.
well, they get to basically what happens is they get to a certain size early on, and they can melt. Then there's enough heat production in the rocks, there's enough radioactive decay that they can melt. And the melting removes the iron from the chondritic meteorites and puts it in the core and leaves behind ultramafic rock or silicate. Yeah.
Right. Okay, interesting. So the short answer to is the moon
To go
or
back.
is
Yeah.
the moon or Earth older? Proto-Earth is older, and Earth is technically younger?
Then the moon, Earth and the moon, let's think of them as the same
About the
age.
same size. Okay.
They're the same. I mean, the rocks themselves are not, but the bodies themselves are the same age. If
Okay.
this, if with our working model of the moon forming by an impact, if that's right, then the Earth and the moon are the same size. They've just had different resetting histories. The moon has
Right.
had very little resetting. The Earth has
Right.
had plate tectonics for a long time, so
Yeah.
therefore lots of
Okay.
resetting.
That makes
So,
sense. And we talk about more in the first part of this follow-up. We
yeah.
talk about what defines the age of Earth, the birth of Earth. So go watch that for more on our philosophical take on this. But
Oh,
you
yeah,
also
yeah, yeah.
mentioned a little bit ago in this conversation the young moon versus old moon. Old moon.
Yeah.
So when was this moon forming impact?
Okay, so you have to think about, I mean, this is a good thought exercise for people to think about. Like, how would you date this process? How would you attempt to date it in any way, shape, or form? And given what we've just described, this moon forming impact, the oldest rock on either the Earth or the moon has to be younger than the moon forming event, right? Than the
Right.
impact, because this was a planetary resetting event. So any
Right.
rocks we find have to be older.
Right.
The ages of the rocks that we find or minerals on Earth, it's like 4.35 or 4.38 billion is the oldest fragment of a little zircon grain that we find on Earth. The oldest rocks on the moon are around that same kind of time frame, like they're 4.35, 4.3 something on the
Okay.
moon are the oldest rocks that we have. So that if you just take that and you say that's the minimum age that the moon forming impact could be, that 4.35 number, that's what I would put into the young moon camp. People would say, okay, that's the age of the moon because that's the age of the rocks that we see is 4.35, 4.38, something like that. That's the age of
Mhm.
the moon forming impact. The other older ages, which are like 4.45 or 4.5 even, these rely on mostly on isotopic model ages, which are saying, I have this rock in my hand that's 4.35. What came before it? And was that a first stage rock or a second stage rock? And if it's a second stage rock, then that means there's a second stage there, which is time. And you can kind of model time, but it's all model based, isotopic model
Oh.
based. I'm not saying it's model based and then it's wrong. It's just
Yeah,
a
yeah, yeah.
different way to kind of approach the question.
Well, could it be
And so
possible that the younger, like actual rock geochemical ages are when that body cooled versus the model ages are when the impact was? Is that a
that's
thought?
true. Yeah, that's exactly right. Did the impact produce some chemical reservoirs that sat there and evolved isotopically, which then
Right.
later on, 100 or 150 million years later, formed rocks?
Right.
Or do the rocks represent the first stages of magma ocean crystallization? And that's the kind of a question that people go to.
Oh.
So there's these rocks called, I love this acronym, creep basalts or creep rocks, which is potassium rare earth element phosphorus rich rocks. Those rocks are what people think are lunar magma ocean crystallization products. So therefore, if that's forming from the crystallization of magma ocean, then when you date that rock, you're dating the magma ocean phase. And there are a group of people who think that that is like 4.35 ish, somewhere around about there, not 4.5 or 4.45. So there's like 100 to 150 million year debate here about young moon 4.35, old moon 4.5 or 4.45
Whoa.
billion years ago. Yeah.
Interesting. Yeah, when you
So
get back that many billions of years ago, you kind of think, 4.3,
yeah,
4.4.
yeah.
But then when you really think about how many years those
Oh, it's
point one is, 100
it's a
million years, that's
massive amount of
crazy.
time.
Yeah,
Massive amount of
yeah.
time. Yeah,
Oh
yeah,
my gosh.
absolutely.
Okay, so the next question you kind of hit on a little bit, but it was how did the moon forming impact change Earth? And how much do we know
Mm,
about what proto-Earth was like compositionally? Had it started to cool and solidify? Was there any crust before this
yeah.
impact? How could we tell? I mean, from what you said so far, it sounds like we don't know because everything was reset. And is
Yeah,
that the case
yeah.
for the moon too?
I think that's right. The everything's reset. It's kind of a short answer. It's a massive planetary resetting event, and so before that, we don't really
Yeah.
know what it looked like. I mean,
Okay.
did it have some crust? Probably. You can't have like a magma ocean planet, and if you think of a magma ocean planet, we often like picture magma oceans, like actually
Right.
oceans, but
Right.
that's not going to exist for very long. You have to have a
Yeah.
super thick atmosphere with like basically a silicate vapor atmosphere
Oh,
to preserve liquid rock at the surface of the earth. That's like what's that got to be, like 1200 degrees centigrade or something. You have to have an incredible atmosphere above that to preserve that temperature on the surface. So most likely there was like a basaltic crust on whatever planets were
yeah.
there, just because it's really hard to maintain for any length of time actual magma oceans like what we think of.
Yeah.
So when
That
we say
makes
magma
sense.
ocean planet, we mean like a thin crust of rock
Okay.
with, we mean a melted mantle is really what we mean by a magma ocean planet, is a
Oh.
melted mantle. So it's a bit
Oh,
of a
okay.
confusing
So
terminology. Probably should have covered that
potentially,
up front, but yeah,
yeah. So
yeah.
maybe kind of like, well, depending on different hypotheses, maybe like Io if it did have the
Right. That's a
melted
good one.
magma ocean. Okay.
Yep, yep,
Okay,
yep, yep,
interesting.
exactly.
And
Yeah.
I'm also curious, given the chemical similarities between the Earth and the moon, do we know why the moon doesn't have an atmosphere or didn't evolve an atmosphere? Is it just the size? It just
It's
couldn't
probably
gravitationally.
that's a great question, and don't. I would assume it's the size, and this is probably a textbook kind of level thing in planetary science that we know, and I just don't know the answer to. I'd
Okay,
guess it
okay.
was had a lot to do with the size,
That's my assumption.
and
Yeah.
maybe Earth's gravity, like attracted all
Pull.
the atmospheric
Right.
stuff away from the moon or
Right.
something like that too. The solar wind, gravity has a lot. You need to have a body of a certain size to keep an atmosphere because the solar wind kind of wants to blow it away all the time. So you got to have
Oh,
some
I didn't even think
gravity
about
to
that.
keep the atmosphere around it. Yeah.
Oh, and actually, that brings up a question. Earth developed its magnetosphere
Yeah.
very early, pretty much immediately, because it would have had the liquid iron,
Yeah, I
sort
think
of.
it again. I don't know what the modeling says for the
Uh,
formation of the magnetosphere. Probably it was pretty early. I know that there's a significant debate in the paleomagnetic community about when the strength of the magnetic field through time, like how early what's the earliest? It's kind of like the early life debate. What's the earliest data point we have that
yeah.
detects a magnetic field, and what is the strength of that
Oh,
magnetic field? So there's a big debate
interesting.
there about whether there's a magnetic field recorded in the Jack Hill zircon grains, for instance, or in
Yeah.
early rocks. Early rocks have been metamorphosed
Oh,
so much it's hard to say, but I don't know the details of the
okay. I
evolution of the
would have
magnetic field.
assumed that it would have been immediate because everything was melted, but I guess the iron has to coalesce and start like
Yeah, and
being in its own.
there's something to do with crystallizing the inner core. Like you got to have an inner core so you
Oh.
can generate the outer core. I don't. I'm speaking
Well,
out of turn. We should
anyway,
talk to somebody else. Yeah,
my
it's a
question
complicated
was
thing.
going to be Earth developed this magnetic field. Does this mean that could the moon have had one if it had liquid iron initially and then lost it?
Another great question. There is, oh gosh, it's a couple years ago I saw a talk on the lunar magnetic field, and again,
Oh,
it's kind of a thing where people debate what the strength of it was. It was probably there, if I remember
okay.
correctly, it was probably there a billion years ago. Going back further, it was hard to tell. So it's a debated literature. There's like very few data points from the
Oh,
moon, but there's
interesting. All
some.
right. Well,
So
anyway, that was just a side question we can have
yeah.
somebody else on to
Well, yeah,
discuss.
that's exactly. I think that's right. I think that's right.
Okay.
Figure
All
out,
right.
talk to somebody who studies this stuff. I think would probably be best to
Yeah.
get them
Yeah.
on.
Well, other than the Proto-Earth, what it might have looked like in terms of crust or magma ocean, do we know if oceans might have existed before the moon forming impact? And do we
Mm,
know how long after impact they started to form or reform?
great question. Okay, the first one, no idea. I would
Okay,
say,
that's what I figured.
before the moon forming impact, we just have no
Don't know
data
anything.
from which
Cool.
to kind of address this question.
Yeah.
The other question depends on when you think the moon formed. So basically, we know that we have pretty good evidence from the zircon record. These ancient detrital zircons, they have an elevated oxygen isotope composition. So the oxygen isotope composition is high. The way you get high oxygen isotopes is by rocks interacting with low temperature water. So that isotopic
Interesting.
signature has been used to argue that there was oceans or water, liquid water, let's say, on the surface of the Earth 4.2, 4.3 billion years ago. To me, that's very compelling. That's kind of like textbook level stuff now. We believe that to be true. So the surface was at a low enough temperature so that you could have liquid water, and you could have liquid water anything 100 degrees C, right? Well, it's not boiling water. It could be hot water, but it's not boiling. It's not atmosphere.
Yeah.
It's not steam atmosphere. So that is 4.2, 4.3, something like that. So it depends on when you believe, if you think the moon forming impact happened 4.35 or 4.45 it changes the time between impact and liquid water on the surface. But I
Okay.
think, the current paradigm has shifted a lot. 20 years ago, probably maybe 30 years ago, people thought of the early Earth as this really inhospitable, hot world. And
Hmm.
now the evidence is pointing towards liquid water on the surface. And
Yeah.
it might have been really hot on the inside of the planet, but the surface was relatively hospitable.
That's what I've noticed as
Liquid
well.
water,
Yeah.
sediments, some thin sediments being deposited. So yeah.
Okay. And another few questions. Also, were wondering or had seen a hypothesis of a potential global ocean. Can we know whether this liquid water was globally widespread?
No. Well, do we know if it's globally widespread? I mean, if one
No.
part, yeah, no. But if one part of the Earth is cool enough to have liquid water, then probably most of the surface is at that temperature, apart from
Right.
big impacts that hit. So big
Right.
impacts could hit, and we're talking not moon forming impact, not planetary resetting impacts, but really big, like,
Right.
hurt the planet but didn't reset it kind of thing. These would create probably transient or temporary temperature pulses on the surface of the Earth. So it would kind
Hmm.
of reset that area. It would make it not habitable in that one area. But if one area on the surface is cool enough, the temperature gradients are probably not huge. So I don't think you're going to have
Okay.
one side that's cool enough to have liquid water and one side that has molten rock at the surface necessarily
Right.
for any
So
long period of time.
theoretically, if those isotope, compositions do indicate that there could have been liquid water at the Earth's
Yeah,
surface at that point, then it could have been everywhere. Like it could have existed in terms of conditions. Whether it did is another question
that's right. So, and
globally.
the evidence here is like 4.2 billion years. We have zircons from one part of the Earth that have elevated oxygen isotope compositions that
Mhm.
indicate low temperature water interactions. So that's one thing. The next data point is 4.0 billion years old in the Acosta and Ice Complex. A different location, maybe a different location, has a similar isotopic signature for water interactions on Earth. So there's two data points. Then you go to 3.8 billion years. There's another rock suite, two rock suites probably at that time interval at least, that have evidence for sediments, banded iron formations, and other types of sediments that are water lane sediments. So that's again good evidence for a large body of water
Yeah.
sitting there somewhere depositing sediments. So basically the idea is we have little hints of a record, and what record we do have indicates relatively low temperature surface
Yeah.
environments, liquid water.
Yeah, and I think it's an important distinction to make that the reason that we have such little amounts of, a grain here, a grain there, isn't because there was little water, is because all of those rocks have gone away or been altered or recycled, or, we just don't have access to
Yeah,
rocks 4+ billion years old. If we had
exactly.
access to all of them, we'd probably see globally, concordant data. So that I think is an important distinction is we just
Yes,
have one grain here, one grain there. That's all we can look at. But
that's
those
right.
grains do indicate these super old oceans. So pretty cool.
That's right. Yes, exactly.
Okay, so we've talked about moon forming impact, could have impacted the way tectonics evolved on Earth, could have impacted the way oceans evolved on Earth. So the follow-up question to that, people were wondering, is could the moon forming impact have sparked life on Earth?
Mm. Um, Unlikely to have sparked life. I think it's probably something that is more a planetary resetting event is probably damaging to any potential life. If it has anything to do with life, it probably reset it in the moment, but then maybe it set the stage again for Earth to maintain this habitable. It created a moon, so it might have had something to do with maintaining habitability for a long period of time. But is unlikely to have sparked life, I think was the word. So yeah, I would say
Yeah,
not.
that's my
Yeah.
understanding as well, is it most likely sterilized the planet
Yeah.
rather than sparked life. But the heat that came from that and the plate tectonics which came later, which aren't directly, correlated with the impact, but that may have played a role in
Yes.
helping life along. And that brings us to our next question, which was, speaking of early life on Earth, a lot of you guys were wondering the timing of the Great Oxidation Event and the start of plate tectonics. Well, one hypothesized
Yep.
start of plate tectonics are both around 2.5 billion years ago. And so a lot of you guys were wondering, is this a coincidence? And I don't know. I don't think we know fully the answer to that question directly, but I do think it's important to note, and I think you mentioned this too, Jesse, in the last conversation we had in the previous follow-up video, is that plate tectonics and life have been very linked throughout time. And it's not just that plate tectonics helps drive these nutrient cycles that drive life, but also that life and the rocks that it produces may, in a way, indirectly maybe, help
Yeah.
drive some mechanisms of plate tectonics. So it's my understanding that this may not be a coincidence, at least the timing of life blooming and plate tectonics starting to operate a little bit more globally. What do you think?
Yeah, I think the life and plate tectonics questions, gosh, there's so many different ways to create like temperature gradients or chemical gradients that could potentially initiate life. But it's more about like creating environments that are good for life to kind of propagate, I think. The link at the Great Oxidation Event, like I kind of said before, I think plate tectonics was operating way before
Yeah.
2.5 billion years old. So I don't think that the GOE had anything to do with plate tectonics per se. It could have something to do with continental emergence and continents kind of emerging above sea level and becoming real stable blocks of land, stable land above sea level. That could
Hmm.
be something that I could see happening more. But yeah, so it's a tough thing to make the link directly, but it's like
Yeah.
the Earth has so many of these feedback loops in it. The carbon cycle, the life cycle. It's rare where one thing directly relates to another, but it's
Yeah.
very common where one thing, through a series of processes, could impact another
Yeah.
process. So,
I
yeah.
did see one hypothesis when I was trying to research for this specific question that suggests this kind of positive feedback loop within specifically how plate tectonics might have helped drive the GOE, or at least this positive
Mm,
feedback loop of increasing the rate of oxidation. It essentially suggests that the increase in atmospheric oxygen initiated by the photosynthesizers might have started to oxidize Earth's mantle, because
mm,
at early Earth was not oxidized, it was reduced, and then as oxygen formed, it started to oxidize all of these chemicals, which is why we call it the Great Oxidation Event. And then as plates were recycled through subduction and through plate tectonic mechanisms, that would have changed the volcanic gases released to oxidized gases instead of reduced
okay.
gases. And that would have caused less oxygen consumption and then finally allowed oxygen to build up kind of on its own, molecular oxygen, in the Great Oxidation Event. So
Okay.
I'm
Gotcha.
curious, and that might have been, happening long before the actual oxidation event when we see the big spike in the atmosphere, to finally allow it to build up on its own. But I don't know. I hadn't seen that before, but it kind of makes sense if plate
Yeah, yeah.
tectonic, if subduction zones began getting more laterally continuous, more larger at the
Right.
time, and more able to bring down that material. I don't know. It
Yeah,
was
I
interesting.
think that's right. Whenever we're dealing with, that's a good point. Whenever you're dealing with the climate feedbacks or atmospheric feedbacks, like you're talking about, the length of a subduction zone matters a lot, and how consistent it's going down. Like how
Right.
much carbon is going down in a trench, like that's a mass thing. What we're dealing with in our signals when we're looking for plate tectonics or mobile lid tectonics going back in time is like, is there chemical evidence for surface stuff getting down at depth at any point in time, right? So in that, as we talked about before, could be like a punctuated subduction
Right.
environment, which has a very different probably impact on the environment and the sort of
Yeah.
global oxygen carbon cycles than a steady state slab, like the
Yeah.
entire Cordilleran system with one slab going down or something
The
like that
more
for
we
tens of millions of
talk,
years.
yeah, the more we talk about the beginning of plate tectonics on Earth, the more that I think it was less the beginning of plate tectonics on Earth and more so an early type of plate tectonics, a middle type of plate
Yeah.
tectonics, a newer type of plate tectonics, and then finally our type of plate tectonics. And I feel like it was, again, more protracted on a smaller scale and then became larger, more laterally continuous. And I think this was a very gradual thing. And it's hard to
Yeah.
put 2.5 billion years or 4 billion. It's hard to put a specific time on it
I agree with
because
that
it's so
completely.
gradual. I
Yeah.
mean, it's a planet. It's not one subduction zone equals plate tectonics. So I think that is a hard thing to talk about, and we can't necessarily put one singular date on it. But
Yeah,
yeah,
I agree
great
completely with that. I
question.
agree completely. Tough,
Yeah.
very tough. It's a great question and a tough one to answer but I think thinking about it, I agree with you. Thinking about it as
Yeah.
a spectrum is definitely the right
But
way
I
to think
do
about it.
have, yeah, I do have a video on my channel that I made about can life induce mountain building, because I saw this paper
Oh,
about
okay.
how organic carbon in the rock record can act as kind of like a lubricant to
Oh, yeah. Okay.
is that, have you seen this? Is
I
this
I haven't seen the one about organic carbon. I've seen it with
okay?
regard to plate tectonic cycles that, subduction zones are kind of lubricated by the hydrated upper plate. But no, I haven't seen that. That'd be interesting.
Oh,
You should send it
okay.
to me. I'd be interested in reading it.
I again, I make these videos and then I forget what I said, so I don't really remember much.
Yeah, I know the feeling.
But I'll link it down below if you want to check
Perfect.
out
There you go.
previous, more knowledgeable Rachel. Okay.
More knowledgeable, Rachel. That's great.
So finally, getting to last couple questions, kind of back to impact related things. Is there evidence for on early Earth? Is there evidence for other collisions, other big impacts other than the moon forming impact? And if so, how do we know how this affected old rocks, first
Yeah.
continents, things like that?
So, is there evidence for big impacts on Earth? Yes, there is. Not going back to the early Earth, though, because again of this planetary resetting
Right. The Proto-Earth, yeah.
process of plate tectonics. So the Proto-Earth, we have no information about that.
Right.
the Earth after the moon forming impact, we have very little information for a very long time. We have big impacts on Earth. We know that the Vredefort in South Africa impact structure, Sudbury up in Canada and Ontario is a big impact structure. We know that these things happened. Our best record for the meteorite bombardment history of a planet, though, comes from the moon. And the moon is the calibration point for the entire inner solar system because we have rocks from the moon. We can look with our telescopes, we can map, and our rovers and stuff, we can map the craters, we can work out the relative chronology of the craters, and then we can potentially date them. So the moon is what we kind of fall back on for our impact record of the inner solar system to
Okay.
calibrate that. And there
Yeah.
used to be this idea of a late heavy bombardment. People call it LHB. Some people call it
Yeah.
a terminal cataclysm that suggested that there's a big spike in meteorites at 3.9 billion years ago. That idea has, over the past decade or 15 years, has been completely squashed, I think. It's safe to say
Really? Oh, I
by
didn't know
the,
that.
yeah,
Okay.
it's one of these weird things that it's still in, it's in textbooks, it's in your like intro level textbook. You'll see some
Right.
stuff about this, but the current planetary science community does not think that this happened at 3.9. There might have been a little bit of a spike at 4.2 billion years old, but there's this diagram, there's this phrase of a sawtooth like bombardment history, which is basically like you had a lot more meteorite impacts very early on and it decreased through time, and you might have had little spikes on it that look like a sawtooth, but basically there's no big late heavy bombardment. That's not
Yeah.
really regarded as a thing. And there's a whole literature on this, and people have written review papers that are kind of talking about how did the scientific community go off in this direction that we don't think there's much evidence for anymore. Like, how does science evolve? It's very interesting to look at. But the late heavy bombardment, probably not a thing at 3.9 billion years ago.
Okay,
Yeah.
interesting.
Yeah.
So there was probably a more consistent, higher rate of
Yeah,
impacts,
almost certainly. And it just
for-ish.
depends on what
Okay,
that curve looks like. And so
right,
for like we published a paper a few years ago where we looked at the zircons, and other people have done similar things from different locations, but zircons can, as we talked about before, can record impact events in their structures. We don't
right.
see any impact structures in the 4 billion-year-old zircons from the Acosta Gneiss complex. So, what does that mean? You can try and do
Interesting.
some statistical calculations, but basically it kind of fits with the no late heavy bombardment model. We don't see it. Does it mean it didn't happen? Not necessarily, but it's
Again,
more
our,
evidence that
yeah,
suggests it probably isn't likely. So there's things like that we can do. But yes, there was almost certainly more impacts further back in time.
right, right.
Um,
But we have,
yeah.
again, limited amounts of rocks and
Limited.
data from that.
Yeah.
So it's hard to
The
tell.
the answer would be go to the moon, sample the heck out of the moon, and then we'd
Okay.
know because the moon has a really nice crater record.
Yeah.
Like we can map the craters really well. We can see here's the big ones, here's the little ones, here's the young one, here's the old ones, and we could go if we could like do field trips to the moon and collect a whole bunch of samples and date them, we'd be able to figure this out.
That's a
So
great point. I feel like the moon is this, like, on Earth, we're like, gosh darn it, we don't have all these old rocks because everything is tectonics keeps resetting everything and
yeah,
recycling everything, and it's so annoying. And then the moon is just sitting there, like, preserving this really old history, and we're like, oh,
amazing
wait,
record.
hey, we
Yeah.
have it. It's right
Yeah,
there.
and it
Oh
has
my God.
a record of what a magma ocean actually looks like. We drill down on the moon, we get a magma ocean record, right? So it has the
Yeah,
records for
that's
the early planetary history sitting there out in our night sky.
wow. Yeah.
Yeah,
Well, we better thank our lucky stars that it didn't involve plate tectonics in an atmosphere. That's
that's right.
great. Awesome.
That's
Um,
that's right.
I did see a really interesting presentation at GSA, or part of one. I probably would be able to explain this better if I saw the whole thing. But I caught part of this presentation where this woman was explaining how they're doing research on early Earth after moon forming impact, but early Earth,
Okay.
Hadean to Archean transition time range of research on the impacts that were happening then, on specific impacts that they have records of, which is very few, but
Yeah.
essentially how they affected or may have affected the evolution or the origin of life on Earth, or at least the conditions that would have potentially supported an origin of life on Earth, which is
Okay. Yeah.
super interesting. And a lot of research that they were doing was pointing to, instead of this idea in people's heads that impacts would harm early life, it may have actually helped provide
Yeah.
these heated hydrothermal areas where life could have started, which is really, really interesting. And I just went on this field trip, GSA field trip, about the KPG impact and how in the crater, life came back soonest because of these hydrothermal ecosystems. And it was really, really interesting. I
Yeah.
would have
Interesting.
thought that that would have been the latest because that was molten for a million years after the impact.
Yeah,
Like,
totally.
yeah, so it's really interesting
Interesting.
that somewhere where the surface was still molten, you could have ecosystem microbial, but ecosystems start to replenish so soon. And that was, of
Mm,
course, after life had evolved. But I don't know. It was an interesting research on early Earth impacts and their link
yeah,
to the
absolutely.
origin of life and kind of early life on Earth. So
Super
I'll
interesting.
link more below about it. But yeah, it was really cool. So last question is, and you mentioned this earlier, how the moon forming impact hypothesis is strong because of the chemical similarities between
Hmm.
Earth and the moon. But some people were curious, are there alternative hypotheses and what is like the evidence for and against these?
So the best supported or the working model for sure is the moon forming impact hypothesis. So the sort of thing that I outlined before. There are other models sort of that they accreted together, like the Earth and the Moon are the same kind of age, and they accreted together, and therefore they would both be like 4.5 something billion years old. Capture that the Moon was kind of passing by and got captured in Earth's gravitational
Oh,
well, that the Moon was kind of spun off of Earth at some level. Those have a lot more flaws, major flaws, critical flaws in them than the giant impact model. So the giant
okay.
impact model matches, most features of the planetary system, and the isotopic similarities are really, and the fact that it has a smaller core is a big one. So the moon forming impact explains the isotopic similarities, the small size, relatively small size of the moon's core. It explains kind of the orbital system, the dynamics of the orbital system really well. And the isotopic similarities are kind of one of the biggest ones, I think, that it's really hard to argue for capture or co-accretion given the isotopic similarities here. So
Okay.
that's my opinion. The isotopic similarities are really compelling for the fact that these two planetary bodies were mixed together at one point in time.
Right. Right. Okay,
So yeah.
so it's still the leading one.
Yes, it's certainly the leading one. Absolutely.
Okay.
The leading,
Okay.
if not the, I mean, I would say dominant.
Very cool.
Yeah,
So
it's cool. It's an arm wavy field. Again, we just talk about arm wavy stuff when we get together here, don't we, Rachel?
I know. This conversation was so interesting. So many things I didn't know, and yeah, sorry to talk a lot about non-Earth things, but there were
Oh
so many
no, it's
non-Earth
great.
questions.
Well, I'm happy to the way like I said, I haven't paid attention to this literature for the last couple of years, so it's fun to kind of rethink through it a little bit,
Yeah.
and go back a couple of years to when I was paying attention to this a lot. So
Yeah, for
yeah,
sure. Well, one last suite of questions that we got on our previous sets of videos
sure.
was specifically the second one was about the Great Oxidation Event, these banded iron formations that formed these BIFs. And we talked a little bit about kind of the very simplified explanation of why they formed, but we didn't talk about, and a lot of you guys asked, why are they banded? And there's a lot that goes into that. And
Oh
you
man.
asked a lot of other questions related to the BIFs and why they formed and the timeline of that. And so if you want us to make, I was going to kind of smush that into this, but it didn't seem relevant to the impact. So if you want us to make another follow-up with potentially another expert to talk about BIFs and how they formed and why they're banded, let us know in the comments below. And also let us know any other questions you have. And if you'd like to see us do more, we're thinking of doing more, answering your question type episodes or long
Yeah,
rants.
absolutely.
So if you like these deep dives,
Long
I
rants,
mean,
exactly. If you
a
like
lot of
long
my
rants with Rachel and Jesse, leave a comment.
we have that. We can do that.
We can
Well,
deliver. Yeah.
a lot of my videos I try to say relatively surface level, make it broadly applicable and understandable to everybody, and I think those are great, but I also love doing these really really deep dives into, newer research and isotopes and whatever, these
Yeah.
very specific details that we as geologists talk a lot about, but the public doesn't get to hear a lot about. So I love to do these, and if you guys like them or want, have any questions you'd like us to do follow-ups on, let us know below.
Absolutely. Thanks, Rachel.